Okay, so let's go and see. We've got this algorithm, yeah, with multiple proposals creating problems. But of all these scenarios, what is it useful for? So I'm a browser trying to go and submit my quiz to Sakai. Will this algorithm work?
You're the only one submitting, right?
I'm the only one submitting? Sure. It's overkill. It has n learners. I have only one learner there. It'll work. Okay? I am Travelocity trying to go and get a hotel reservation. I'm trying to get a plane reservation from 2 different airlines. It won't work because? Somebody who has an answer, please. This today? Okay. Somebody who has answered. Somebody who hasn't answered? Nobody? Okay. So who wants to answer now? Brennan, have you answered today?
I think so.
Okay. So Sam, what's the reason?
Yeah, it won't work because you could be double booking in places because you might, reservation might change to a hotel or something like that, and it didn't tell everybody. Someone else who tried to book finds out later. And so after they say, hey, I want to book that. So 2 people want to book a hotel at the same time, but they don't communicate, and then they both try to book, but the message that is booked doesn't come to the other guy. And,
So what happens, let's take this transaction that I am Travelocity, and I say I want, I want to go from here to here for this much money. Can it just unilaterally go and send a message to all three sides, etc., saying, hey, take the value? So there's multiple proposal problem, but what's going on here? One of the proposals will go. So let's say the proposals are all being serialized at Travelocity.
then it would be okay, I guess.
So they're being serialized at Travelocity, so we don't have multiple proposal problem.
That would be fine. Let's go through a centralized route, relay or whatever it is. So that
As long as there's only one proposer, yes, it's fine.
yeah, that would put
Everyone else is just on there.
But remember, Travelocity has to contact 5 other sites. Why is it contacting those sites?
If you have, say, a hotel and a flight that are, linked together, and you're supposed to be sold in a package, and you have one user, the hotel books for one proposal, and then books the same flight for another proposal, you could get in some sort of deadlock position where it can't propose, where one proposal is for each book, and then you can't switch it.
So in our algorithm, we just send the learn notification. So deadlock occurs when we wait. We're not waiting. So that is not a problem. Okay, Nick?
The problem I thought would happen was that, say you want to, say Travelocity goes to American Airlines and books stuff, but American Airlines also listens to stuff outside of Travelocity, and those people could, and we can't guarantee those eventual consistency happening at the same time. So when Travelocity goes, say it goes to check the hotel first, and while it was checking out the hotel, someone else booked directly to American Airlines and booked out the only left ticket, and then Travelocity goes to that plane ticket, wouldn't be able to get it, everything breaks loose, and
Okay, so the problem is this, that Travelocity went and found out what the prices were from all the 5 sites, showed them to you, you said book, and when it goes now to Hilton, it says, no, sorry, that was 2 seconds ago, right? And in this method, there's no way for somebody to say sorry to the proposer, okay? And Travelocity might say, Hilton may say yes, but American Airlines may say no. So there is only a learn. There's no way of accepting, deciding whether to accept or not. There's the feedback kind that I was talking about. We need that feedback kind now. Okay, so we can't use this simply because there is no vetoing way to veto. Okay, and with multiple changes, I mean, we are not going to get anywhere. Locks, again, multiple changes, we are not going to get anywhere. Physical mirroring, Akamai?
Like one or many learner.
Many learners, and they're just slaves, they're just readers. Yeah. How about master-slave replication? That I'm the master and the slaves are I'm replicating the slaves. Single master.
Yeah.
Same as Akamai? Brennan?
Yeah, I think it's the same, but I don't think the next one will be.
But can you think of a reason why it's not the same, that you might not want to unilaterally...
You can take over for the master?
Yeah, slave can take over, sure. And when the slave takes over and the master fails and the master comes up, does it need the help of the slave?
Yeah.
We saw it might need the help of the slave.
Yeah.
So why might it not work in that case? Yeah, Matt?
If the master goes down, would you have multiple slave proposals to take over?
Yeah, so let's not, that's another issue. We can all decide that the lowest numbered slave takes over. So we can all decide that consensus problem easier. Okay, so in that case, why will this algorithm not work when the slave is going to help with the master coming up?
You can't come back, yeah, and so the slave can't tell master what data it holds. So you can only accept data and change whatever the slave holds.
Yeah, but then Sam?
Like maybe a master, there's two slaves. The master shares the state with one person and crashes. Someone becomes the master, but the master and the slave are now not the same. And then when this master comes back up, there's two different states that it can look at.
So if the master dies right after sending the message, but before the message reaches the slave,
And they're all out of sync after that.
then out of sync, and more important, when the master comes up, there's no guarantee that, if they need the slave state, there's no guarantee the slave has that. So this is something that's very configurable in the real systems. Okay? And the answer is yes and no. Okay? If the master just comes up with the log file, you don't have to wait. Okay? But if you MySQL has something called synchronous and semi-synchronous and asynchronous replication, and this is asynchronous replication, where there's no shared time at all, so that's. But if you need some more guarantees, then you will go and share with the slave before proceeding. Okay, and of course master, as Brennan was pointing out. Okay, so does it solve our original problem that we are trying to go to war against an enemy, and you want to decide at what time the war is, the battle's going to start, at dawn or dusk or some other time? And will the learner mechanism work in that case? What does that mean? That the general sends a message to the other general and changes his state, and assume that the messages are received reliably.
As long as there's only one general.
There's one leading general. The messages are reached reliably from host to host. That means this guy will reach the other mountaintop. Is that enough? I didn't tell you how long he'll take. If he reaches after dawn, we're in trouble. How about, do we know the general actually read the order? This is a process on some machine. We just know the TCP IP delivered the message to the kernel. Do we know that the process actually got scheduled? Right? So, this is called eventual consistency or asynchronous replication. Okay? Do not know when messenger reaches, and the problem is compounded with end receivers. Okay? And do not know if general has looked at the message. Okay? So, how should we modify this now?
I mean, if the issue is whether he's looked at it or not, can you just, after they have viewed the message, then just send a call back to the other?
Send a message back. That's going to be the solution. That's one solution, right? Let's assume that that is not the question. Let's try to solve the problem in incrementally. What if the issue is, has the guy reached before dawn or not? So how to decide, to have an estimate of when, that's all we want to know. We want to make sure that we don't change the state, we change the state at the right time. Okay, the hosts assume that the general will look at it immediately. Can we avoid that extra message? And we can make assumptions. Okay, we can make so. Let's try to define the problem a little better. Okay, so asynchronous value replication or eventual consistency. How might I define that formally? Suppose t is the time at which I propose a value. What does eventual consistency say? Let's say D is the set of all replicas.
Like after someone after t passed with some amount of time, we guarantee they have the same replica.
Okay, sometime after t.
Yeah, sometime, but we don't know how.
Some t1 after t, which is less than infinite. Right? So commit PD where D is some replica minus propose submit of P or propose of P submit of P is finite for all the replicas. Right? How would I define synchronous replication then? That we're all in sync. Our consensus values are always in sync. They all replicate at the exact same time. Okay? So state IT is equal to state JT at all times for all pairs of IJ belonging to the set of all processes. That's what synchronous replication really means. Right? And what Matt was suggesting didn't quite give us this. With that extra message, it didn't quite give us this thing. Okay? So, did I make a mistake? By the way, this is all, I did this all from first principles. There can be errors. Is there an error here? There might be. Huh? When you guys study, look at it, at some point, please let me know if there are errors or not. But this is something, like I said, it was easier for me to come up with this myself than to try to find a source that defines it the way I'm presenting it. So, how can I guarantee synchronous replication? And you can make any assumptions you want to. Yeah.
Without the general.
And including having a global clock. You can make that assumption too. You can make anything. Imagine a square wheel. Okay? So you can just make any assumptions you want to. I just want to know what assumptions we need to create a synchronous application. Yeah. Brennan, you want to try it? Because, yeah.
You could try and do something kind of like link state flooding.
Link state flooding, okay.
Networking, which is when you want to propose a new value, you send it out to all the learners.
Yeah.
And then the learners, if they're receiving multiple proposals, they have a local timestamp associated with their state. And then if the state that if the proposal that they receive has a timestamp newer, then they update. If it's older, then they do nothing.
Okay, so we can send multiple learners, but that send multiple messages, and you're saying if the messages duplicate in some way, we ignore it. But how do I make sure that at all times my consensus state is identical? Nick?
So in the database sense, you need two-phase logging, not two-phase logging to assume that.
But that's you're coming up with jargon right now that we don't understand. And two-phase commit and two-phase this thing is not going to solve the problem as it turns out.
Basically, you restrict at all times, at all systems, you restrict it's only going to be one proposal that's handled atomically, and it's always handled. So if there's like multiple outstanding proposals to handle for kind whatever, you always choose the small.
But you guys are coming into the multiple proposal issue, multiple learner thing. I'm just saying there's a one proposal. This is one general, multiple things, and all I want to make sure is the consensus state are identical at the same time. I'm not trying to resolve conflicts. And if you're going to rely on messages being sent back and forth, we never know. We come into the impossibility problem we came up earlier. At some point, some guy will change the value. How do we guarantee that at exactly the same time the other guys change the value if you're going to send a message?
You lock it at two and then release it.
Fine, you locked it at two ends. Now, at some point, I will change the value at one end.
Yeah.
How do I make sure the same point time all the other guys change the value? How do the other guys know that I changed it at this time? If the time I change it is unknown to the other guys. Yeah, Sam?
You don't change your value when you send it? So
Okay, you don't change it, so when do you, at some point I will change the value.
you propose a change, but you don't make the change yourself. You wait for everyone else you propose the change to.
How do I know that they've changed it?
They call back.
Okay, they call back, so how do they know that I've changed it?
They don't.
They don't receive another.
So how do we make sure that our values are sync at the same time? I want to make sure when I change the value, you change the value.
Maybe real time or like.
Yeah, at each time t. If the time at which I change is unknown, let me just sort of say, if that is unknown, let me try to prove a theorem here.
You can't do it.
You can't do it.
It's like the general thing.
It's the general problem. So the solution is to somehow know the time when I change it and make some assumptions about time. Okay? Okay? And so we create a synchronous system, which will be unreasonable to some degree, but that's we'll be getting. So we'll get to that next time. Okay, so this is where we were last time. As Matt mentioned, Matt asked the question, is synchronous replication impossible? So we'll start by trying to answer that question. So remind you, asynchronous versus synchronous. Asynchronous is eventual consistency, which means ultimately, if everything stops, all activity stops, all replicas within finite time will be consistent. Okay? And we saw that maybe that's okay for mirrors, that when you are making a change, the mirrors can take their time in updating themselves. And then we try to define something that's not asynchronous, and we called it, we called it synchronous last time. I'm going to call it pure synchronous. And the opposite of asynchronous, we try to define easily. And we try to have a nice definition, or easy definition, or simple definition, I should say, and says at all times the states are always the same. Okay? So if we define it as that, we seem to be getting in trouble. Okay? We had a long discussion, and there were many algorithms proposed, which are all practical algorithms. In fact, you guys implemented in assignment 3 a non-asynchronous implementation, right? So it was not asynchronous, but it was not quite this synchronous. Okay? And it all involved a site that is proposing a value, sending messages to other sites saying invalidate your values, doing 2 phases, and then sending the actual value after the invalidation phase. Okay? But that was not exactly what we have here. Okay? And we kind of argued that it seems impossible because everybody has to be in sync. So unless everybody knows when the first value will be changed, they don't know when to change their values. So everybody has to know the exact value to change, time at which they should change the value. If they don't, then one will change before the others. Because one will change, then will communicate that it has changed to somebody else. That will take some time. and then they will change. So there will be some time period when the values are out of sync. Okay? So if the time at which the first value is communicated first value is set has to be communicated, then we can't achieve that kind of synchrony. And before we kind of go into what assumptions we can make to make that happen, I didn't mention what the set D was. Okay, so I said all replicas in set D, where D is, have the same value. So can there be some doubt and mystery about what the set D is? The D is a set of all distributed replicas.
Yes, if someone joins late or leaves.
Someone joins late or leaves or dies, involuntarily. So the question is, what is D? Okay. So for now we'll assume that the process will eventually start, and so we'll assume that there's some fixed number of replicas, and if somebody dies, they'll eventually start again. So we know what D is. But in general, they may not rejoin. We might increase the set of replicas, and we might make do with fewer replicas than we initially had. So that's a tricky issue that is not addressed that much in the literature, in a lot of the literature. Okay, so okay. So let's go back to synchronous. Assume that it's static set for now. Okay, and how can we achieve synchrony by making some assumptions? Okay. And you can make any assumptions.
I mean, so it seems like the assumptions that you need it to transfer immediately, and you need a reliable connection. Sure.
Okay, so if it could take 0 time to send a message, then indeed, good, excellent. Then can we still achieve synchrony? We can, because we immediately send the value and they're all in sync. Okay. And if we can't make that assumption, so that's, I said you can make any assumptions. You got me. Can we make
Okay, so when you meant to be 0 time, if you knew the exact time.
if I knew how long it would take?
Right,
Okay, supposing, so what's the maximum time it would take, or?
just if you knew how long it would take to receive it, you could send it ahead of time.
Okay. Okay, so if all sites took the same amount of time, okay, then that's equivalent to what he's saying, right? That seems to be more reasonable than his assumption. Then we could go and send it ahead of time, or we could just change our value exactly t seconds later. Okay, supposing it takes variable amount of time. So we're trying to make it a little bit more realistic. Good, excellent.
As kind of an extension onto that, if we know how much the maximum time is going to say, then have everyone set it at like the maximum time. Like whatever the longest path is, have everyone set it when the longest path is.
That's interesting. So I am somebody, and I know it takes 2 seconds to reach you and 5 seconds to reach him. Okay? So when should I'm sending it at unit 0. So I'll change my value at time?
5. You would be at 0 and I would be at, was that 2 or 3 2?
Okay, so I will do it at 5. You know exactly how long it took to, okay, so you will set it at what time?
3.
And he set it at what time?
0.
If it takes 3 to you and 5 to him?
3 to me, then I would set it at time 2 for me. He would set it at time 0 for him, and you would set it at time 5 for you.
I guess what he's saying is you can just establish a clock time that if you do, and in 5 seconds, everybody's going to have it, and I'm going to wait to update until.
And then you do like that max time minus.
I understand that if I knew what the max time was, if I send it at time 0, I will set my value at time 5, right?
Mhm.
Okay? I'll send you a message at the time 0, right? You will receive it at time 2.
You should change it. Then you should change it back to.
So you'll receive it at time 2, right? When will you set your value? How do you know to set it at 5? So in the message, I will go and say, okay, I know that each site, I know exactly when they will, exactly what the time is. So, okay, this is even more general. That I know exactly how much time each site will take. I communicate all these times to all the sites, and they appropriately set the time. That's fine. It's better than what was proposed. Yeah, more general. Okay. Let's say we can't make that assumption.
Can we assume that there's a universal clock?
Okay, let's try to do that. Okay, because if we start doing that, we come to a class of systems that has been studied a lot. Okay, so in asynchronous value replication, we know that things aren't happening at the same time, right? So this is happening. So we can assume there's a global clock. We can assume there's an upper bound on successful message transmission time. Okay, we don't exactly know how much time each message will take, but we know there's an upper bound. Okay, and normally when people make these assumptions, they don't look into scheduling issues. They just assume each node is one process and it just instantaneously receives a message. But let's be more realistic that there's also some time that will be required at the other end for the process to be scheduled. Okay, so let's assume there's some upper bound TS, which is the scheduling time. Okay, John, so I've given you all the assumptions you need. Tell me what I should do now.
Well, I mean, if everyone has a universal clock, the sender sends it at 0, and then everyone will have it by time t. So everyone sets it at time t on the universal clock.
Okay, and so supposing the time, okay, so I can't control time. At time 15, my user tells me propose a value. So we can't decide at what time the proposal will happen.
You said like in t seconds, everybody change, and they set it up, because you know it's the upper bound.
So I know T is the upper bound. I send a message to everybody,
Yeah.
and I tell them, okay, here's my value.
Change at time t. Like
Change at time what?
current time plus t.
Okay, so my current time plus t, I change my value at my current time plus t. When I send the message, okay, supposing I send the message at time 15, and t is 10.
Okay.
I will set it at time 25, right?
Yeah.
I'll send you a message now.
Yeah, because you assume it's a global synchronized clock.
Fine, it's a global synchronized clock.
Yeah,
So at time 10, what did I say? Time 10, I set it at 15. At time 15, I send you a message. It will take less than 10 seconds.
Yeah.
Okay, what are you going to do when you receive the message?
So the message itself is going to include so to speak, like the set time for this action, which will be 25. So it's 15 plus 10 as your upper bound. And everybody, it's basically telling like everybody says at 25. And 125 counts, everybody says.
Okay, so that's good. So what I'm saying is I send the time at which I set mine, right?
You will send it.
Yeah.
No,
Oh, either way.
yeah.
Either way, because we know what the max time is. So I send information about my time, and then you use your current time and my time, and the actual time it took to transmit, and the max time it will take to decide when you will set your value, right? Okay, because you know when I set it, you know when you received it, you know the difference, okay? And then you know how much time, when exactly I will send the value, so you will go and set your value at that time, okay? Sounds good?
Yeah, also I think that that's some of the one of the strategies they actually use in this shoot.
Okay.
It's like assume the time in the future and then everybody change it until then.
Yeah, but I have to also communicate, so it's not that we can assume that time 0 this will happen.
I mean, the point is that assume you're going to change in some point in the future and then, communicate what you want and everybody will get that before that future point and then when it comes, it is.
Okay, so you're saying that future time, what I'm trying to say is that the future time, I might not know when I will get a proposal. I might not even know whether there will be a proposal. So I can't predict the future time, but I like what you've proposed already, so we don't have to we don't have to relax that. That we will send my time. We will send. We will send. We all know the maximum time, and we know. The receiver knows when they will receive the message. So we have enough data to go and figure out when to set our time. Okay, and what I show you is a much simpler scheme, which is. I don't know if anybody's even proposed this or implemented this for sure. I will just assume there's a clock ticking on each computer. And if a message comes in, I'll just delay sending it to the next clock tick. Okay? So I don't have to send my time. And we know that the message will be received before the next tick. So each receiver will go and set it at the next tick. Okay? So this is simpler. It requires less time to be sent, but I like your mechanism better because it uses resources better. Okay, so what we've done is, do you guys like this mechanism, by the way? In fact, I like your mechanism better than this. This is simpler than yours, but I liked yours better.
This is
So if your upper bound for the receiving time is longer than a clock tick, then you're in trouble?
Yeah, we'll make sure that, no. I made my clock tick equal to the upper bound. Okay, and yeah.
So any messages received within that clock tick will be processed, it'll appear, I guess, in the
Next to next.
What's that?
If a message is processed before clock tick I, that means after I minus 1, it'll be processed in clock tick I plus 1. Yeah.
One thing I'm not sure how you deal with is how do you deal with concurrent proposals?
We are not even trying to deal with conflicts. Okay. Okay, and why is this impractical?
Because you can never synchronize.
Okay, because you can't have a synchronized clock, but I still like your proposal better than this, and why is that? Assuming that we can have synchronized clocks.
You don't delay sending.
You don't delay sending, you don't delay receiving. Well, you do delay receiving, but you don't delay sending. Okay, so that's. But in your case, you send more information. Okay. So worst case T is very large, so that's a problem. Even in your proposal and mine, we delay. Okay, and worst case T may be very large. Okay, and so this brings out an issue I wanted to bring out. Global clock is unreasonable, which I mentioned. Okay, actually that issue we'll talk about a little later. So given that global clock is unreasonable, let's go back and try to change what we want. Okay, that we are not going to have a pure synchronous replication. Okay, we're going to have something that's useful for our applications, but it's not going to be synchronous. It's not going to be asynchronous also. So can we have a more complicated definition of what we want as the opposite of asynchronous so that our implementation is more realistic? Or to put it in other words, what did you guys exactly implement when you did assignment A3? What kind of replication was that? How would you define that? It was not 1, it was not 2, it was not asynchronous, not pure synchronous. So what did you guys exactly do? What did you really guarantee? And the key is that you guys invalidated your state. That's the key. That in first phase you invalidated, in the second phase you reach consensus. So the state can not only be a regular state, it can be an invalid state also. So we don't want to just consider state values, we want to consider that in our definition. Yeah.
Can you say exactly what's in there as synchronous plus it either has to be equal or it is just unset or as you said, that's poison, whatever.
So what you want to say here is that my state is either equal to your state
Or not set.
or one of us is not set. Okay? So, and let's go and look at a practical application. Let's say we are changing the protocol, okay, that we are using to communicate. So I want to change the protocol. And what will I do? For a while, I will just not send you messages while we're trying to figure out the change. So, but I do want the sending protocol and the receiving protocol to be the same. Right? I don't want them to be different. If they're different, then I'm not either receiving or not sending. So it's basically, so if they're both set, they should be the same. Okay? So while messages in transit, sending and receiving protocol at proposal are not the same. Okay? So with pure asynchronous, that can happen. Okay, that I might receive message using one protocol, that was sent using one protocol, I might be sending a message using another protocol. Okay? And invalidate the protocol rather than pure synchronous. Okay? So what we'll do is, I'll call it synchronous invalidation, replication, and state IT is, if it's not equal to null, okay, then state JT is equal to null or state JT is equal to my state. Okay? So given my state, if my state is not null, then other people's state is either null or is equal to my state, which is what Nick said. Okay? Sounds good? Again, this I've come up from first principles, so there may be mistakes here. So look at this with care. Okay? Sounds good? Yeah, Brandon?
So in our implementation and assignment of 3, we
Yeah.
didn't handle the case where we had like multiple proposed changes with this.
No, we are not dealing with multiple at all right now. Okay? We are dealing with it by saying we'll allow them to happen and pray that everything goes well. Okay? So this is purely meant to create a synchronous system. Okay? Assume there's only one proposer. Okay? And even then we do want a synchronous system. Okay? So now we needn't assume a global clock. Okay? And what we can do is a version of what you guys did earlier. That what should I do now? I propose the value at site 1. I can go and what should I do at this point? Okay, invalidate. And now what should I do? I do want, okay, what should I do now? This is one phase. I don't want to do two phases. I'm assuming there's no global clock, but I'm still assuming an upper bound on how much time it will take for the message to be sent. John?
So invalidate yourself, send to everyone else, and then after the max time, validate yourself.
Yeah. Okay. So invalidate yourself. Wait for time t before you set it. During that period, send the message to everybody else, and they all wait time t. And then at this point, they're all pending, and then one by one, they reach consensus. Okay. So again, the problem is the worst case t is large. But we didn't have extra messages. Okay, we just had one round. Yeah.
Why do the others have to wait?
Actually, that's a good point. The others did not have to wait. They would just make it.
Yeah.
No. Wait a minute.
They have to wait just in case.
They have to wait
you
too.
haven't changed your state yet.
Because
I mean, regardless, you're gonna have some people that are changing before others. So if you don't have the others wait T, you'll be the last one.
No.
If you do have them wait T, they'll be the last one.
No.
Regardless, you're gonna have someone being the last.
No. So here's the deal. John's saying that why not at site 2 change it immediately, and at site 3 change immediately. If you change it immediately at site 2 and site 3, then
Their state's not.
their states are not the same.
I mean, but your delta between the time between each of them updating their state is the same. It's just shifted way to the right because they're all like still waiting the same amount of time.
But they're waiting in the pending state.
Oh, yeah. Okay.
We never want a situation where in the protocol case, I receive a message that has been sent using one protocol, and I'm sending a message using another protocol. So you're saying, okay, guys, wait for everybody to invalidate.
Yeah, so you basically like have all the four T's overlap with each other so that during that whole union of time, you will guarantee your presumption.
Yeah, so you do need two phases in this thing. We want consensus, then everybody goes to null, and then everybody goes to consensus. That's what we want. And I'm achieving these two phases without sending messages in two phases. Okay? Okay. So assuming this works, the problem is that the worst case T is large, right? So even if we would wait only at the proposing site, we still have to wait somewhere. Okay? And as it turns out, we have to wait everywhere. And this sort of brings out a trade-off that's often mentioned in these systems. You want safety, and that's one goal. Okay, safety means we want some kind of constraint. So what's the opposite of that goal that conflicts with it? Performance. What did you call it? Latency. Latency. Latency is one aspect of this whole thing. So we want safety versus progress / liveness. Okay, so we want things to occur as rapidly as they can while being safe. Okay, and things are not as rapid as they could be. Okay, so and this is where what you guys now we'll go to what you guys implemented and what many of you proposed last time, that we will not just have one round of messages. Okay, in the asynchronous system we had just one round of messages. In this one phase synchronous system, we had one round of messages with waits. We will now have not only proposers and learners. Okay, so in our system, the learners and proposers are all one set. But in general, we could have one set be the learners, one set be the proposers, and they may be overlapping or different. So we have a learner set, we have a proposer set, and then we'll have also a set of acceptors. Okay, they are the ones who will get accept messages, and the accept messages are the ones that will invalidate the state right now. They will do other things later. Okay, so you send a message to all the other sites, and they'll send responses to tell you that this phase is over. We need to know when this phase is over before we begin the learn phase. Okay, so you need to get the messages from these acceptors, and once they've accepted your messages and invalidated, then we'll send the learn. Okay, which is exactly what you guys did, right? You had this phase where you made remote function calls to each of the sites, waited for the response, and then you made these asynchronous procedure calls for the learning part. Okay? All right? Okay. And let's just see how this works. I propose a value. I execute the accept method in my own site because I'm also an acceptor, which means I make it pending. And then other sites make it pending. Now they're making it pending based on not passage of time, but the receipt of the accept message. And they send the response back. And I accumulate responses. Okay? I've accumulated another response. We accumulated another response. Now I've got all the responses I want, I needed. So everybody's pending, I know. So now I execute the learn call. I make my state consensus. And I send a message to the other sites. Okay. Questions?
So does this require that the replication site number one has to know exactly how many things are connected to it?
Yes, it has to know how many acceptors there are. It has to know who the acceptors are. And since it's also sending messages to the learners, it has to know who the learners are. Exactly. Yeah, and in your system, they're all, and in almost all practical talks about these things, they assume that these sets are the same. Okay, but they can be different. And why not present them orthogonally, separation of concerns? Why try to make them sets the same when they needn't be? But in practical applications, many practical applications, all three sets will be the same. Okay, the learner set can be different from the acceptor set. Okay. But yeah. Okay, questions? And if the learner set is separate from the acceptor set, then the synchrony requirements on that set also become less stringent. Because if we're just sending, if they never invalidate the state, then they are not obeying our rule. Okay. So let's just look at the algorithm. Our algorithm says propose, send accept request to all acceptors instead of notification to all learners. Okay, that's what my propose is doing now. Okay, my propose initially just sent notification to all learners, and acceptors will usually include self. And if learners can be asynchronous, then they may not be the same set. Okay, so our propose is simple. Our accept, invalidate the state, and send response to sender. Right? That's what we did. And now we have to come to accepted. Okay, so there's 3 calls here. There's the propose call, there's the accept call that you make remotely, and there's the accepted call that is called by accept back to the proposer.
So you have 4 calls.
Yeah, so there's many calls. Yeah.
So you just send the learn.
Yeah, and then there's learn. Right, very good. Okay, so accepted, what will it do? You could receive a notification. If there's not sufficient notification so far, just accumulate them and return. Right? And if they're sufficient, then send the learn notifications. Yeah.
Are we assuming right now that the acceptors can veto?
Next thing. Can acceptors veto or not? Okay, but we're coming to that. We've got the whole infrastructure. We're sending these messages. Why not increase the range of applications we can support? So that brings us to, so we've solved the leading following general problem. Okay, we've got synchronous consistency with the following general. We both know when to attack. But what if the other general is not just following general, can think also and can decide whether we should do it at that time or not? Okay, so you send the message and the guy can say no. Okay, so we allow veto. How would we modify the previous algorithm to allow vetoes?
In that case, if you see even one node, it's just the whole thing is gone.
Okay, so now the accept call can return a no. It doesn't just say I'm done, I've invalidated the state. It says, you know what, I've invalidated the state, sure, but my vote is no. So maybe it's a veto, maybe it's not a veto. Okay, and the proposer accumulates all the no's, decides what to do with them, and then sends the verdict to everybody. Okay, that's more general than what you said. Okay, yeah.
So in that case, even if it is vetoed, you still need to send it to every location with the original value, since their state was invalidated.
So even if it is ultimately, so firstly the word veto is a little misnomer here.
Or if they say no.
But yeah, but ultimately, if ultimately the message is rejected, then you can do 2 things. You can just say no news is bad news. The value remains, so that's not good. If the value remains pending, and they can't use the old value, so you have to send the learn notification with the current feedback. Okay, but there are some systems where the value is used only once. In which case, once even if you don't, that means there is no old value, and if there is no old value to use, then you may not even send a message back. Okay, you say, okay, that proposal is just quashed, nothing happened. No listener method is called, so no action is taken. Okay? Questions? Okay. So the question is, what if it's receiving general vetoes, and the problem is compounded with n vetoing generals, and so again, veto is a misnomer here. Rejects, I should have said rejects. Okay, and if you have n people rejecting, then we have to decide, whether we are considering each rejection a veto or we are going to take a majority. So that's an issue. Okay, So now we have feedback from accepts, and we have learns that have negative information also. Okay? So you can propose, execute accept here, pending, you say yes, you proposed it, you agree to it, you send a message back, you send a message, it says no perhaps, maybe this is not a veto, so you accumulate the no's, you get another no, at this point you say, yeah, I've heard enough no's, so I'm going to just send a no to everybody. So you decide that your state is consensus, you send it to them, their state is consensus, okay? Send it to them, their state is consensus. So is this synchronous replication now? You see that the last process has not even received the accept message. Number 4 has not even invalidated a state. And yet everybody else has consensus.
It's fine, because it wouldn't have changed anything. Even if you send it, it wouldn't have changed. It wouldn't have changed.
So even though the message is not being received, when it is received, it's not going to change the value.
Yeah.
Okay? So even though 4 is not received, invalidating accept request, its value is correct. Okay? So we are saved in this case. Okay? So it receives a learn notification. And the interesting thing is, it receives a learn notification before it receives the accept request. So your implementation becomes much more complicated.
Then you mess up.
Sorry?
If it happens in the diagram, like it shows, you basically messed up before.
No, I didn't mess up 4. The 4 receives it. Oh, you're saying I can't
If
have.
you did it this way, you would have messed up 4, right?
No.
You could have said,
What do you mean by messing up 4?
So you say, so the learn that's coming into 4
Early.
says, do not change, and stay as consensus, and accept comes in, make it invalid.
Yeah. So my accept is smart. My accept says if the value is not pending, I just reject it. Okay? By the way, would this situation occur with TCP/IP?
No.
It wouldn't occur with, so many of these algorithms don't assume message ordering. But this situation wouldn't occur with TCP/IP because your accept request will be received before. Okay? But in any case, at some point, we hadn't received the learn notification and we had, reached consensus at other sites. So that was maybe an issue, but it's not really an issue. Okay? Okay, so that's what happens here. Let's try this now. I propose a value, I accept, make it pending, I say yes, I receive another yes, I receive another yes, and I say at this point, you know what? I go for majority. I don't care what the other guys think. I'm going to say yes. So I change it to 42. Consensus. Consensus. And now do we have a problem? The consensus values are different. Okay? And the last one is still behind. So this is not synchronous replication. Okay? So we had asynchronous, we had pure synchronous. Now we have this synchronous with invalidation. Then the third one was synchronous with invalidation. Now we need a fourth kind of replication. And what would you call it? It's not my term. Okay, so we'd call it semi-synchronous. Okay, and do you want to define semi-synchronous? So consensus value is different. Okay, and again, I'm assuming here out of order, but that won't happen in real life. So I've got synchronous replication defined. Can you define semi-synchronous replication now? and make it different from asynchronous and synchronous and pure synchronous? I'm not exactly asynchronous. I am, yeah.
I guess you're kind of saying at some time everybody will catch up, but it's not guaranteed to be at the same time.
Okay, so if I say at some point people will catch up, that is true, but that's also asynchronous. So how do I distinguish this mechanism from asynchronous? John?
Well, I mean, the difference between this and the last one is you just have the majority that needed to be synchronous. So you've got the majority synchronous and the rest are asynchronous.
Okay, so what we do is, the synchronous is relative to some set. And in the previous one, it was set D, set of all known replicas. And now we'll make it some set E, where E is a subset of D, and E is not empty. Okay? And whether the E is majority, 1, 2, who knows, that will be various shades of semi-synchronous. Okay? And this is a term I've actually, I Googled and I found there's from MySQL reference manual that they actually have something called semi-synchronous replication. And in fact, I first Googled for Facebook replication. I tried to figure out what they do. And they said, we do semi-synchronous replication. And that was like a very big deal, they were saying, because they were no longer doing asynchronous replication. And so there was somebody's interview that was mentioned. So I Googled for semi-synchronous replication and found, and they said we're using semi-synchronous replication in MySQL, I think. So I looked at MySQL reference manual and they defined it. They didn't quite define it this way, but this is the way I interpret what they said. Okay? So now we've got yet another form of replication. Okay? So like I said, E is some subset of D and E is not D. Okay, so in our system, there is asynchronous, there is all synchronous, which is what we were calling synchronous. Okay, that means everybody we're considering 2 people, proposer and maybe somebody else. That was one of the algorithms that was in MySQL. It could be majority synchronous, or it could be some custom synchronous, who knows. So the point is, there's multiple shades here.
Is 2 synchronous pure synchronous, or what is?
No, 2 synchronous means me and at least one other person.
Oh.
And that makes sense, right? If I'm doing backups, I know at least somebody else has my data. Okay? So that's exactly what the Facebook guys were saying, we are using now semi-synchronous. Okay? So that the other slave can now catch up and change if the master fails. Okay? So 2 is an important point. We could have 2, 3, 4, 5, 6, 7, whatever, but 2 is an important point. Majority is an important point. If we are expecting failures, then we say, okay, we'll take the majority vote there, and custom could be anything you want. Okay, okay, questions? So what's majority in a dynamic set of acceptors? Okay, I kind of assumed static before, and that's a very interesting issue. And when I was implementing, I didn't know what to do. Okay, so I've got 3 choices: the current members that are known to be alive. Okay, we take majority of them, or we take all of them. The initial members that came up. Okay, and we're saying, okay, we expect the initial set is 5. We want at least 3 to be voting yes before we accept a value. And if one of them dies, we still want at least 3 because we think 3 is a good number. 3 is a sufficient number. Okay? Or we could have the maximum members. If things gradually ramp up and go down, then we say, okay, it's the maximum members. Okay? So these are so again, this thing is not very well defined in some of these algorithms. In some of these systems, they expect only 1 slave and 1 master. So that's an easy number to choose there. Okay. Okay. So now my accept changes. Now that I have negative feedback. Not only do I invalidate state, I also calculate the verdict. Okay, and I send verdict to sender. Okay, so my accept is changed. My propose hasn't changed at all, so I'm not even showing it. Okay, accepted. If not sufficient notifications, record notification return and send learn notification. That is already there. Now what do I have to do? I have to deal with negative results also. And I could deal with the negative result immediately, or I could deal with it, accumulate the negative results to see how many there are, right? Now also, since I could, so why do you think I had this step? If proposal not pending, return. Could it be that I could have a not pending return, a not pending proposal? When an accept request comes back? We have semi-synchronous replication also as a choice, right? So we saw that 4 hadn't even received the accept request before you decided to learn something, right? So we have to make sure that we don't do anything, okay? Now see whether you can make sense of this. This was a subtle point and it took me some time to come up with. If some proposal has rejected and it's an all synchronous replication, then that is a veto.
Yes, need full consensus.
Because we are basically saying that we need full replication. Okay? We are then considering it to be a veto. Actually, we could still consider it not to be a veto. We could still want to consider. Then.
If you get one no, you basically fall inside it.
So I'm saying that here, right? And now that I think about it,
But that's not
so the question is, I'm tying the vetoing and the synchronousness together. Okay? I'm saying, and maybe I didn't get the implication right here, if you're not pure all synchronous, okay, then you can't have vetoes. Because you're not even waiting for everybody. If you're not waiting for everybody, how can you have a veto? So you can have a veto only if it's all pure synchronous. That's what I want to say, but that's not exactly what I'm saying here. Because I'm saying, if you're full synchronous, then it is a veto. No, it may or may not still be a veto. So maybe we will, I should say, then maybe reject proposal and maybe send. So maybe it should have been before the reject and not learn notification. Then maybe reject proposal and then maybe send learn notification. Because we may not want it to be a veto even then. We do want full synchronous. We want everybody to know that the state is invalid right now, but we are not vetoing. But certainly if it's not synchronous, then we can't support a veto because we're not waiting for everybody. Okay? Yeah.
So if you have an all synchronous replication, so one failure results in the failure of the entire consensus. If one member sends a no, wouldn't they would already know they would have failed. So would they?
No. If they fail, so what does failure mean? Failure. Okay. So you're saying
the proposal.
Okay. So they know that they failed, so they could.
Do they even need to learn?
They don't need to learn, but the other guys need to learn, right? Yeah. So you can optimize and not send a learn notification to the one who rejected. But maybe they don't know what the master's behavior is.
Right.
So why bury that into the slave? So we let the master decide and let them keep it invalidated too.
Okay. Yeah.
Okay. But these are all edge cases that you want to think about. Okay. So now what can happen is that the proposal can be group rejected. Okay. So then you send negative learn notification and return. Okay. Okay. And let's just look at this in code. This is my accept. Accept again can, like I said, we might get a learn before our accept. So if it's not a pending thing, we just do nothing. We do nothing if maybe we are still expected to reply. If you're still expected to reply, we send a reply back, but we make that a parameter. Okay? We calculate the feedback using some method, check accept request, and if it's not success, and we have to send a reject notification, then we return. We don't have to send a reject notification, then we return. Okay? So maybe the other side is just going to time out. So we let that also be a parameter. Otherwise, we send the accept notification. Okay? Questions? Okay, now by the way, record and send, look at this method accept, it is a void. It doesn't return a value. Let's assume, I've tried to make this stuff independent of Gypsy, okay? And that's part of the reason why I don't have a return value and we're not assuming a remote procedure call. But for a moment, assume that we're using remote procedure call and calling accept directly. Why am I not just returning a value in that case? Or why not return a value in that case? I'm going to argue that even in that case, we don't want to return a value. Now, we don't want this to be a function. We want it to be a procedure call. Well, if it's asynchronous, we won't have accept called. You see in the code here, sometimes I don't send back a notification. Right? There are cases when I don't send it, yeah.
I mean, we don't know if we have consensus yet, so we don't want other parts of the program to use that value.
No. So remember this. Yeah, indeed, we don't have consensus. But you see that I send accept notification as a last step. Why not send that back as a value of this return value of this accept method rather than as a separate notification? Indeed, we don't know if there's consensus or not. Especially if we don't know there's consensus, we want to send that value back. But you see here that sometimes we know that this is going to be, a veto, like you were saying. So that's the exact reason why we may not want to make this a function call, because sometimes we don't send back a notification. Okay? And we'll see later an algorithm where we will get the accept request from one computer, and we'll send our verdict to other computers. So this level of indirection, this level of flexibility you get from not making this a function call. Okay? So do not want to tie it to RPC. That's part of the reason why I didn't make it a function call. Caller may not wait for response. Okay? So caller may not wait for each individual response. It might wait for only majority responses. So I don't want the caller to have to wait for each guy's one by one. Okay? Or have a separate thread for them. And response may be sent to others than proposal sender or not be sent at all. Okay? So that's a subtle point, implementation point. Okay, questions? Yeah.
I'm a little bit unclear about some of your Boolean methods. What they do, like is send, accept, reply for resolve proposal.
Sorry, yeah.
Like what is that?
So say that again, is send, accept, reply. Okay, so if the proposal is not pending, that means it's resolved, right?
Yeah.
The question is, if it's resolved, did I get the Boolean wrong? And you don't need to send a reply for resolved proposals, then don't do anything. Otherwise, send the reply anyway.
Oh, so there might be some case where you do need to send it for a result?
Maybe the other guy's counting and waiting,
Okay.
So, like I said, when you don't know the answer, you may say parameterize it. Okay, so I don't know for sure whether that should be the case. So I'm just saying, hey, I've got a flexible mechanism, and by default, you do send the reply back. So I've not even tested it with the other value. Okay? But like I said, lots of papers talk about not sending back negative news, only sending positive news. Okay? So I'm being consistent with that. I personally think that there should always be a reply back just to make sure that everything is, there's more information in the system. Okay? And now my propose. If you remember, I had a dispatch proposed, then I had a dispatch proposed that decided whether it's called local propose. And I've got this scheme that allows acceptances. But I don't have to use it. I just have this new implementation. And we can now have parameters saying, do you want to use its full power, or do you want to use its partial power? So I have a little parameter saying, if it's asynchronous, just send learn notification. Don't even go through the accept phase. But if it is synchronous, then send the accept request. Okay, so I have more flexible mechanism. I can use the the asynchronous mechanism directly, or I can add my own stuff to it. Okay, so in my implementation, synchronous is a subclass of asynchronous. So I'm just allowing the superclass behavior here. Okay? Question? Okay. And this is the most complicated method, okay, because now I have to accumulate acceptances, right? So this is the method that's called in the notification sent by the accept request. So I, as a proposer, made the accept call. The accept call sends an accept notification back rather than returning a value, and then notification is sent, but results in the accepted method being called. And we get the feedback, and again, you know, if we don't need this feedback, we just return. If it's not pending, we return. And this is following the algorithm I showed before. If it's negative, if the feedback says that success was not achieved, then if it's all synchronous, I say process accept rejection. Okay, which, you know, is again, this is assuming that these two things are tied together, which I think in practice they will be. That if it's all synchronous, it will be a veto, but it needn't be. So this is less flexible than it need be. Otherwise, we aggregate the accepted notification, right? Questions? And aggregate notification calls another method to say, okay, with this notification, do I have sufficient acceptors? Okay, and can you guys sort of figure out what the three cases of sufficient acceptors are? So I test if sufficient acceptors is a capital Boolean rather than a primitive Boolean. And I did that deliberately. So maybe the method is, yeah, John?
I mean, you need like 3 values instead of just 2.
Yeah. What are the 3 values I need?
Null, true, and false.
And the null means? Yeah, right.
Maybe null means that you've not received enough to be like a majority.
Null means that?
Yeah, and then false.
Sorry, no. So no means no or null means.
Null.
Null means what?
Like you've not received enough to make a definitive decision about what to do.
So you haven't received enough to make a definite decision. If it's non-null, we've received enough information, and now the decision can be one way or the other. Okay? So if we haven't received, we just accumulate. Otherwise, we send either success or we send back an aggregate denial saying, hey, you know, the consensus is that it's not a veto, but it's an aggregate denial. Okay? Questions? Yeah.
So I'm just trying to understand why you would return. If it's equal to null, then you don't know a null. So
You're just waiting for another aggregate method to be called later. You're just counting. And you're not counting in one procedure. This procedure is being called multiple times. So it keeps the count in some instance variable. And sufficient acceptors looks at that variable. Okay? And that variable is tied to the proposal number. So you know. Okay, let's just, to make this more real, you know, given that people can reject, what may be the reasons for rejecting, and why we might not want asynchronous replication. I just took something very relevant to what I was doing currently to illustrate that. So, and I think I mentioned this before, why do I not want asynchronous? Well, I make a change to my PowerPoint. This is my typical workflow. I'm working at home. I'm making changes to the last moment, and I get tired, and I say, okay, now this is the time I'm going to take my drive. So I have to shut my laptop. But I have to be very careful before I shut my laptop, because I have to make sure that the file has been synced at Google Drive. Otherwise, all my last night work and this morning work will not be here when I resume my work here. So that's why I want some kind of feedback. Okay? Yeah.
And from a commercial standpoint, you would also want to, make sure that they're not going over their memory capacity or whatever.
So there may be an error.
Yeah.
Okay? That's an important point. So if you look at this, it says view 5 unsyncable files. So what I could do is just keep my laptop on, and expect that before the power saver comes on, my data are sent. But it may not be synced. And you see I have 5 unsyncable files right here. Okay? And then there might be a concurrency conflict also, and I'd like to know about that. Though of course Google Drive is going to be mostly good about that and create a new version for the conflict. Okay? So reason for not accepting. So want to know file has reached server before shutting down laptop. Want conflict to know not cause inconsistent files, and want to know if file actually savable by server. Okay? And there might be not enough memory. There might be a bug, which is, I believe, the reason why I have these errors. Or they claim that the reason is that I was trying to upload a file to a directory to which I had no access. Okay? It might be correct, but I suspect it is not. So, but these are all reasons that you can have. So, in the proposal feedback kind, I try to cover these cases. Okay? Aggregate denial we saw, that is something that the consensus mechanism puts in. Then, the individual service might go and put service fault, access denial, whatever. And you can see that these values correspond somewhat to the proposal state values. Okay? And what I would love to, but proposal state has more values. It has consensus and pending also. What I would love to have is one enumeration being a subclass of another enumeration, so that I can just add some more values. And I've had to really deal with adding, whenever I think of a new name or a new name or a new value, I have to add to both. Okay. Now here's the question for you. So which of these checks are made by the application, Google Drive, knowing whether it has enough space or not? And which of these checks are made by the consensus mechanism? So which one of these values are set? I've got a choice of proposal feedback kind. Which of these values are set by the application and which are set by the mechanism?
One's having to do with the actual consensus or set by the application. So things like access denial are from the application check.
Okay. And which is from the consensus?
Something like
Concurrent operation and
aggregate.
aggregate denial. Okay. So that's abstraction, and it's also aggregate denial. So now let's ask a software engineering question. How does the application get involved in this stuff? So far this was all the abstraction code. How do I let the application get involved?
Pass messages of chain to a higher layer.
So pass a message to a higher layer, which means invoking a callback. And we already know about a callback, a listener callback, which is already there, right? That's how the application knows that a value has changed. How would this callback be different from a listener callback? The listener, you tell it, here's something that happened. What's the difference here? Yeah, it's returning a value. And if a learner callback you call to announce a change, this callback you invoke to check if the change has to be made. So it's like you're making a change. After a successful change, you call the listener, and before the change you call, and this is a common design pattern. Anybody know a term for it? So it's the vtor pattern. Okay? So you can have add consensus listener, you can have add consensus vtor. And the vtor here means that particular site, you see, you can have multiple listeners here. Similarly, you can have multiple vtors registered at the particular site. And at a particular site, if you have multiple vtors registered, then any one of them can veto. Okay? Ultimately, aggregately, they may not, when you look at the responses from all sites, you may not consider that to be a veto. But from the point of view of an individual site, in this design pattern that I'm talking about, any one of the vetoers returns false, it's a veto. Okay? So what happens here? My check proposal for accept, what it does is says check with vetoer. Okay, this is at the individual site. Okay, and the vetoer goes through all the vetoers, and if any one of them says not success, then returns from the loop and returns the first veto that it got. Okay, so if you just Google for property change vetoer in Java, you will find more or less this pattern. There they throw an exception if there's a veto, which doesn't make sense to me because veto is something you might expect in regular, veto does not mean an error necessarily. Okay, so this is what happens here. Okay, and since we do have an implementation, let's just go and see this working. So this is acceptor 3. It's passive. It doesn't veto anything or doesn't reject anything. So it just gets information. So it got it. So since it doesn't veto or reject anything, it sent the accept notification as success for 29. But it got back an answer saying, sorry, somebody else rejected it, and that was considered a veto. So it got that response. Okay. This is the guy who questions things, and this is acceptor 4. So it sends a notification of service denial at the top, and then it gets back an echo saying that your service denial caused a complete since this is synchronous replication, and in my all synchronous in my implementation, any rejection is a veto. When it's all synchronous, you get a proposal service denial. Okay. This is a more interesting case. Here, I sent a proposal and I got the first notification back, and I called the method sufficient agreement checked, and you see here that I'm printing out certain numbers separated by vertical bars, and you see these numbers change. So do you want to tell me what these 4 numbers might be? So I have 1144, 2244, 3344. Yeah, Raman?
Well, the first number is probably count.
Count of?
Number of, forgot what we've been calling them. Basically, the recipients of the message.
Okay, so the count of how many accepts have occurred? How many notifications you got?
Yeah.
Okay, so one of the numbers is a count of how many notifications you've got. You need to keep that count to know whether we've got enough notifications to make a decision. Okay? Yeah.
And the other ones, like how many said success or not?
How many said agreed with you? Okay? So we need that count too, and they're both increasing. And what would the other two numbers mean?
Max, or the total, how much you need.
How many, out of how many do you need? Okay, so that's one number. What was the last number?
Maybe how many you sent?
How many you sent? Or how many alive nodes there are. Right? So good. And number of agreements, number of notifications, number of current members, number of total members considered in our thing. Okay? So there might be only 3 alive. We might have sent only 3, but we might have to consider a majority out of 7 or 4. Okay? And one of them is not alive right now. So I'm keeping count of all 4. Okay? So at some point we have enough, and we send the learn notifications saying, and we get and receive the learn notification about that change. Okay. And this is rejected proposer. They're also keeping a count. So far, every notification was a success. Yes, yes, and then finally we get a service denial, and we say, okay. That means it's vetoed. So I go and send, I send a service denial request, reply. Now this is something different. That was all synchronous. This is 2 synchronous. Okay. So now again I'm keeping a count in the accepted proposal in the proposer 2. So I get 1 count that is correct. I get another count. So now I get a denial, right? I got 2 notifications back, but I got only 1 agreement. Okay? But I don't consider that to be a veto because I wait for more, and at this point I get enough, so I send success. Okay? So this is just showing you the two synchronous case. So I just ran the same program, changed the replication synchrony, and got this result. Okay? And here's something that caused me to pause for a while. It's a very small thing if you're a theoretician, but being a systems guy, this was quite exciting because I learned something new here. So I'm counting, okay? I get one success, I get another success, and I declare, that's enough for me to declare success, right? So I go and declare success. And the interesting thing is, I count another time, even though I should not be counting, and I declare success yet another time. And I said, what did I do in my code? I check for pending. So why am I flooding the system now? There's even more. Why am I doing this? And the key is, and another time, I guess I was supposed to, my red lines have got unaligned. The key here is that when I declared success, I sent a learn notification to everybody, right? Including myself. It is the learn notification that changes my state from pending to non-pending. My learn notification is scheduled much later, as you see. It says, right, the second from the bottom, it says proposal learn notification received. So at that point, my proposal became not pending and not earlier. Okay? So I was excited because scheduling makes a difference here. Okay? And I changed my code. I said, okay, I better make sure that I change the state. I called my learn in the thread that got accepted rather than in a separate thread to be scheduled later. Okay, so in the thread that invoked accepted, I changed it. Okay, I thought I changed these. So, by the way, sometimes I feel that the PowerPoint placement is not what you see is not what you get. So what I sometimes create in the PowerPoint is not what I display in the show. But this may be one of my mistakes here. Okay, so what happened was I changed the state immediately. So now you see sufficient agreement checked here, checked again. And learn notification sent, and then learn notification received, and state change immediately. Okay? So I didn't. This in the previous slide that occurred much later. Okay? And now I'm not sending duplicate learn notifications. Okay? Questions? Okay. So now the later responses are just ignored. They're not calling sufficient agreements checked. Okay, because the proposal is not pending any longer. Okay, so we have done semi-synchronous and synchronous consistency, and now we can do a little bit more. So can we do nested transactions now? Travelocity, I have to check with Hilton, I have to check with American Airlines. I need to check. Okay. If I'm the only proposer, sorry? All synchronous. What, so I can do that now. Okay. For master slave backup, if I go and look at these systems, some of them say we want asynchronous, sometimes some say semi-synchronous, some say synchronous, but now we can do them all. Okay.